You're watching the most important month in human history unfold, and most people don't even realize it. Right now, as you're listening to this, 3i@TLS is racing toward a moment that will determine whether humanity gets its first permanent interstellar neighbor or watches another cosmic visitor disappear forever into the void. October 29th. Mark that date. In less than 4 weeks, something unprecedented will happen behind our sun, hidden from every telescope on Earth. And according to Harvard astrophysicist Avi Loeb, that timing isn't coincidence, it's opportunity. The perfect moment for Atlas to execute what he calls a reverse Oumuamua maneuver, using our sun's gravity not to accelerate away from us, but to brake, to slow down, to trap itself in permanent orbit around our star. Think about what that means for a moment. Every interstellar object we've ever detected has been a brief visitor. Oumuamua streaked through in 2017 and vanished. Borisov did the same in 2019. They came, we got a few months to study them, and then they were gone forever, back into the cosmic dark where we'll never see them again. But Atlas might stay. The mathematics of this decision point are breathtaking in their precision. Right now, Atlas is traveling on what's called a hyperbolic trajectory, moving faster than escape velocity, destined to swing around our sun and shoot back out into interstellar space. But orbital mechanics offers a narrow window of possibility. At perihelion, the closest point to our star, the sun's gravitational field is strongest. This is where spacecraft execute Oumuamua maneuvers, firing their engines when moving fastest to achieve maximum efficiency in changing their trajectory. But here's what makes Atlas extraordinary. While most spacecraft use this technique to accelerate, to gain speed for journeys to the outer planets, Atlas could theoretically do the opposite. A reverse Oumuamua burn, fire engines to slow down instead of speed up, bleed off just enough velocity to transition from a hyperbolic escape trajectory to an elliptical bound orbit. The physics is elegant, the timing is perfect, and the implications are staggering. Loeb has calculated the numbers with characteristic precision. Atlas needs to reduce its velocity by approximately 2.3 kilometers per second at perihelion to capture into a stable orbit. That's not a massive change about the speed of a high-velocity rifle bullet. For an object massing 33 billion tons, it would require substantial but not impossible thrust. And the energy requirements? Well, within the theoretical capabilities of advanced propulsion systems we can barely imagine. But here's where the timing becomes almost suspiciously perfect. October 29th isn't just when Atlas reaches perihelion. It's when Earth will be positioned on the exact opposite side of the Sun. We'll be in what astronomers call solar conjunction, the Sun directly between us and our potential visitor. Every ground-based telescope will be blinded by solar glare. Even space-based observatories will struggle to peer through the Sun's brilliant corona. If you were designing a trajectory that allowed you to make a major course correction unobserved, this would be it. The optimal moment for orbital mechanics, combined with the perfect blind spot for observation. It's the kind of timing that makes Loeb raise his eyebrows and wonder if we're looking at intentional design rather than cosmic coincidence. The decision Atlas faces, if it is indeed capable of making decisions, represents a fundamental choice about the nature of interstellar exploration. Leave, and remain a mysterious visitor that tantalized humanity for a few months before vanishing into legend. Stay, and become humanity's first confirmed interstellar neighbor, available for extended study, possible communication, and whatever purposes brought it here in the first place. This binary outcome carries profound implications that extend far beyond astronomy. If Atlas leaves, we add it to our catalogue of curious interstellar objects and wait for the next visitor. Business as usual, with a few scientific papers and some interesting data points about comets from other star systems. But if Atlas stays, everything changes. A permanent interstellar visitor fundamentally alters humanity's relationship with the cosmos. We would no longer be isolated in our solar system, wondering if intelligence exists elsewhere. We would have a neighbor, something that chose to remain in our vicinity, available for extended observation, potential interaction, and whatever agenda brought it across the light years to our doorstep. The scientific opportunities alone would be revolutionary. Instead of a few months of frantic observation before losing our target forever, we'd have years, possibly decades, to study Atlas in detail. We could dispatch robotic missions to intercept it. We could attempt communication. We could analyze its composition, structure, and behavior patterns with unprecedented precision. But the darker possibilities lurk just beneath the surface of these exciting prospects. If Atlas possesses the technology to execute precise orbital maneuvers, if it can choose to stay or go based on strategic considerations, then we're not dealing with a passive object of scientific interest. We're dealing with something that makes decisions, something with objectives, something that might be evaluating us as much as we're studying it. Loeb doesn't shy away from these uncomfortable implications. In his recent interviews, he's been increasingly direct about the need to consider both benevolent and hostile scenarios. An advanced civilization capable of interstellar travel might arrive as explorers, scientists, diplomats, but they might also arrive as assessors, determining whether a newly technological species represents an opportunity or a threat. The timing of Atlas's potential orbital insertion adds another layer of strategic significance. By arriving during solar conjunction, by making its critical maneuver when Earth's most advanced astronomical facilities can't observe it, Atlas would demonstrate not just technological capability but tactical awareness. It would show understanding of our observational limitations and the strategic value of operating within them. This is why October 29th represents such a pivotal moment in human history. Not because we know what will happen, but because we'll finally start getting answers to questions that have been building for months. Will Atlas emerge from behind the Sun, on the same hyperbolic trajectory it entered with, or will it reappear on an elliptical orbit, committed to remaining in our solar system for the foreseeable future? The uncertainty is both thrilling and terrifying. We're approaching a cosmic decision point with implications that could reshape humanity's understanding of its place in the universe. And we're approaching it largely unprepared, without protocols for dealing with potentially technological interstellar visitors, without international consensus on how to respond, and without clear strategies for the various scenarios that could unfold. But the clock is ticking. Atlas continues its relentless approach toward perihelion, carrying with it the power to transform human civilization's relationship with the cosmos. In less than 4 weeks, we'll begin learning whether we're about to gain our first confirmed interstellar neighbor, or watch another mysterious visitor vanish into the darkness between stars. The mathematics of Atlas's potential capture into permanent orbit read like a precision-engineered ballet of celestial mechanics, where every variable aligns with almost suspicious perfection. To understand why Loeb considers October 29th such a critical moment, you need to grasp the elegant brutality of orbital dynamics and how they could transform a passing visitor into a permanent resident of our solar system. Right now, Atlas is following what astronomers call a hyperbolic trajectory, a path that carries it around our Sun and back out into interstellar space, with more than enough velocity to escape our star's gravitational embrace. Its current trajectory has an eccentricity greater than 1, the mathematical signature of an unbound orbit. Without intervention, Atlas will complete its swing around our Sun and disappear forever, joining the vast population of objects drifting between the stars. But orbital mechanics offers a narrow window of possibility that has captured Loeb's attention with its precision timing. The Oberth effect, named after German physicist Hermann Oberth, describes how rocket burns become most efficient when executed at the point of highest velocity in an orbit. When you're moving fastest, when kinetic energy is at its peak, a given amount of thrust produces the maximum change in orbital energy. For spacecraft departing Earth, this principle drives our entire approach to interplanetary travel. We fire engines at perigee, the closest point to Earth, when velocity is highest. The energy we add gets multiplied by the existing kinetic energy, producing dramatic changes in trajectory with relatively modest fuel expenditure. Every probe we've sent to the outer planets has relied on this fundamental principle, but the Oberth effect works in reverse as well. Just as you can add energy most efficiently at perihelion, you can also subtract energy most efficiently at the same point. A reverse Oberth maneuver uses the period of highest velocity to brake rather than accelerate, bleeding off speed when the effect is maximized. It's the technique you'd use if you wanted to transition from an escape trajectory to a bound orbit with minimum energy expenditure. For Atlas, perihelion occurs at approximately 1.4 astronomical units from the Sun, just inside the orbit of Mars. At this point, it will be traveling at roughly 54 kilometers per second relative to our star. The precise velocity reduction needed to capture into an elliptical orbit depends on the desired orbital parameters, but Loeb's calculations suggest a delta V of approximately 2.3 kilometers per second would be sufficient. That number might sound modest. After all, it's less than 5% of Atlas's perihelion velocity. But when you're dealing with an object massing 33 billion tons, even modest velocity changes require enormous amounts of energy. The kinetic energy that needs to be dissipated equals half the mass times the velocity change squared. For Atlas, that works out to roughly 8.8 quaternions 10 circumflex 22 joules, equivalent to the energy output of our Sun for about 30 seconds. Yet this staggering energy requirement becomes manageable when viewed through the lens of advanced propulsion technologies. Ion drives operating at high specific impulse could theoretically achieve such velocity changes given sufficient time and electrical power. Fusion rockets could do it more quickly with higher thrust. Even more exotic possibilities like antimatter propulsion or electromagnetic field manipulation could make such maneuvers routine for a sufficiently advanced civilization. The timing of Atlas's perihelion passage adds another layer of precision to this scenario. October 29th isn't just when Atlas reaches its closest approach to the Sun, it's when Earth will be positioned 180 degrees away in its orbit, placing our planet on the exact opposite side of our star. From our perspective, Atlas will be in solar conjunction, completely hidden behind the Sun's brilliant disk. This geometric alignment creates a perfect observation blind spot during the most critical phase of any potential orbital maneuver. Ground-based telescopes will be useless, overwhelmed by scattered sunlight. Even space-based observatories like Hubble and Webb will struggle to observe anything within several degrees of the solar disk due to instrument safety protocols and the overwhelming brightness of our star's corona. The duration of this observational blackout extends the window of unobserved operation considerably. Atlas will disappear behind the Sun in mid-October and won't re-emerge until late November, more than a month of complete invisibility from Earth's perspective. During this time, any number of course corrections could be executed without our knowledge, but the most intriguing aspect of this potential orbital capture lies in what comes after. If Atlas successfully transitions to a bound orbit around our Sun, its new trajectory would determine its future relationship with Earth and the other planets. Loeb's preliminary calculations suggest that a successful capture could result in an elliptical orbit with a period of several years, bringing Atlas back to the inner solar system repeatedly. The orbital parameters of such a captured trajectory would reveal important clues about intent and capability. A highly elliptical orbit with aphelion beyond Jupiter would suggest a conservative approach, remaining far from the inner planets most of the time, while making periodic close passes for observation or resource assessment. A more circular orbit within the inner solar system would indicate a bolder strategy, maintaining closer proximity to Earth and the other terrestrial planets. The energy management required for such orbital maneuvers also reveals technological sophistication. Natural objects follow predictable paths determined solely by gravitational forces. Any deviation from these predicted trajectories indicates the presence of non-gravitational forces, typically outgassing for comets or solar radiation pressure for small asteroids. But the scale of velocity change needed for orbital capture far exceeds what natural processes could produce. This is where Atlas's apparent resistance to non-gravitational acceleration becomes significant. Despite clear evidence of outgassing, the James Webb Space Telescope measured material streaming off its surface at roughly 150 kilograms per second. Atlas's trajectory shows virtually no deviation from pure gravitational motion. This suggests either a much more massive object than its outgassing rate would indicate, or active correction for the perturbations caused by gas emissions. The implications of successful orbital capture extend far beyond the mechanics of celestial motion. A permanent interstellar visitor would represent humanity's first confirmed neighbor from another star system. Unlike brief flyby encounters that provide only weeks or months of observation time, a captured Atlas would remain available for extended study, potential communication attempts, and whatever purposes brought it to our solar system. The strategic advantages of permanent residence in our solar system are substantial. Extended observation of Earth's technological development, detailed reconnaissance of planetary resources, establishment of a forward base for future operations, all become possible with a stable orbital platform. From a purely tactical perspective, permanent presence provides options that brief transit visits cannot match. But perhaps most significantly, successful orbital capture would demonstrate technological capabilities that firmly place Atlas beyond the realm of natural phenomena. Natural interstellar objects don't execute precision course corrections. They don't time their maneuvers to coincide with observational blind spots. They don't choose to remain in star systems they encounter by chance. If Atlas re-emerges from solar conjunction in late November on an elliptical orbit around our Sun, we'll know that something with advanced propulsion capabilities has taken up permanent residence in our cosmic neighborhood. The question then becomes not whether we're dealing with technology, but what that technology wants and who controls it. October 29th represents the decision point, where these possibilities transform from speculation into measurable reality. The 33 billion ton mass calculation isn't just a number, it's a constraint that fundamentally challenges our understanding of what Atlas could be and how it should behave. When Loeb and his colleagues published their latest analysis, tracking Atlas's motion with unprecedented precision across 227 observatories worldwide, they weren't just measuring trajectory, they were weighing evidence that pushes this interstellar visitor into territory where natural explanations begin to strain credibility. The method they used is elegantly simple in principle, but devastatingly precise in execution. Every comet experiences non-gravitational acceleration as gas jets off its surface, creating tiny rocket effects that nudge the object slightly off its predicted gravitational path. By comparing Atlas's actual position with where it should be, if only gravity were acting on it, astronomers can measure these perturbations and work backward to determine the object's mass. For typical comets, this calculation is straightforward because the non-gravitational effects are easily detectable. Comet 67 Churyumov-Gerasimenko, studied extensively by the European Space Agency's Rosetta mission, showed clear deviations from its predicted orbit due to outgassing. These deviations allowed scientists to estimate its mass, density, and internal structure with remarkable accuracy. But Atlas defies this standard model. Despite clear evidence of active outgassing, the James Webb Space Telescope measured material streaming off its surface at roughly 150 kilograms per second in early August. Atlas's trajectory shows virtually no deviation from pure gravitational motion. The upper limit on its non-gravitational acceleration is less than 15 micrometers per second squared, an almost impossibly small value for an actively outgassing comet. This presents a fundamental physics problem. Gas jetting off one side of a comet creates thrust. Just like a rocket engine, conservation of momentum demands that the comet experience an equal and opposite reaction. For Atlas, with its measured outgassing rate, the expected acceleration should be easily detectable with modern astrometric techniques. The fact that it isn't suggests only one possibility. Atlas is far more massive than any interstellar object we've encountered before. The mathematics are unforgiving. Given the observed outgassing rate and the absence of detectable trajectory perturbations, Atlas must weigh at least 33 billion tons to resist the rocket effect of its own gas emissions. That's not an estimate or a rough calculation. It's a lower bound. The true mass could be significantly higher. To put this in perspective, 33 billion tons represents roughly 1,000 times the mass of the Great Pyramid of Giza. It's comparable to a small mountain, compressed into an object perhaps 10 to 20 kilometers across. For a natural comet, such extreme density would require composition unlike anything we've seen in our solar system, perhaps solid metal or incredibly compacted ice and rock. But there's another interpretation that Loeb finds increasingly compelling. What if Atlas isn't solid? What if those 33 billion tons are distributed throughout a largely hollow structure, like a massive shell or framework, rather than a dense, homogeneous mass? This possibility transforms our understanding of what we might be observing. Spacecraft designers have long understood that efficient structures maximize strength while minimizing mass. The International Space Station, despite its enormous size, weighs only about 450 tons because it's mostly empty space enclosed by relatively thin walls. Even terrestrial engineering follows similar principles. Modern skyscrapers are essentially hollow frameworks that achieve tremendous height, with surprisingly modest material requirements. Applied to Atlas, this engineering perspective suggests intriguing possibilities. A hollow or partially hollow structure could easily achieve the 33 billion ton minimum mass while maintaining internal volume for what? Equipment? Fuel? Living spaces? The speculation runs wild, but the physics remains constrained by observation. The surface-to-mass ratio implications are particularly fascinating. If Atlas is indeed a hollow structure, its thermal properties would differ significantly from a solid object. Heat distribution would be uneven, with the thin outer shell heating rapidly while the interior remained cold. This could explain some of the unusual outgassing patterns observers have noted, materials sublimating from the surface, while the bulk of the object remains stable. Moreover, a hollow structure would have different gravitational signatures than a solid mass. While we don't have the precision to measure Atlas's gravitational field directly, future close approaches might reveal density variations that betray internal voids or structural elements. The way sunlight reflects off its surface could also provide clues about shape irregularities consistent with artificial construction. The material science implications are equally intriguing. Building a structure capable of surviving interstellar travel requires materials with extraordinary properties. It must withstand micrometeorite bombardment, radiation exposure, extreme temperature variations, and the mechanical stresses of acceleration and deceleration. These requirements suggest advanced composites or metamaterials far beyond current human capabilities. Yet the surface composition detected by spectroscopy shows relatively mundane substances: water ice, carbon dioxide, simple organic compounds. This apparent contradiction suggests that whatever Atlas is made of at its core, it has acquired a coating of interstellar material during its journey. Ice, dust, and organic molecules would naturally accumulate on any object traveling through space for millions of years, creating a camouflage layer that makes artificial structures appear natural to casual observation. This masking effect has precedent in our own solar system. Many asteroids are covered with regolith, a layer of pulverized rock and dust created by eons of micrometeorite impacts. The surface composition often differs significantly from the interior, which can only be revealed through deep drilling or catastrophic collisions. For an interstellar visitor, this natural camouflage would be even more pronounced after eons of travel through cosmic dust and gas clouds. The engineering challenges of maintaining structural integrity over interstellar distances are staggering. Any artificial object would need to be built to last not just for the journey, potentially millions of years, but also for operations upon arrival. This suggests either remarkably durable construction or active maintenance capabilities that could repair damage accumulated during transit. Active systems would require power sources capable of operating for geological timescales. Nuclear reactors might provide such longevity, but even they have finite lifespans measured in decades rather than millennia. More exotic power sources, radioisotope, thermoelectric generators, fusion reactors, or even antimatter systems might extend operational lifetimes to match the requirements of interstellar travel. The 33 billion ton mass also places constraints on the propulsion systems that might be embedded within Atlas. Chemical rockets would be hopelessly inadequate for moving such mass efficiently. Ion drives could work, but would require enormous power systems and extremely long operating times. More advanced propulsion concepts, fusion rockets, antimatter drives, or even speculative technologies like field propulsion become necessary to achieve meaningful acceleration. But perhaps most significantly, the mass calculation provides a reality check on the technological hypothesis. 33 billion tons isn't arbitrary, it's the minimum required to explain Atlas's observed behavior. This constraint eliminates many speculative possibilities while supporting others. A solid natural comet of this mass would be extraordinarily rare and difficult to explain through conventional formation mechanisms. A technological artifact with this mass becomes more plausible, especially if it represents the infrastructure needed for interstellar missions. The weight of evidence quite literally pushes Atlas toward the technological end of the spectrum. Not conclusively, not beyond doubt, but significantly enough that dismissing the possibility becomes increasingly difficult to justify scientifically. October 29th will provide new data points, but the fundamental mass constraint will remain. Whatever Atlas is, it weighs at least 33 billion tons, and that alone transforms it from curious anomaly into genuine mystery deserving of our most careful attention. When you start stacking the probabilities, Atlas begins to look less like a cosmic coincidence and more like a carefully orchestrated arrival. Each individual anomaly might be explainable through natural processes, but the cumulative effect creates a statistical profile that challenges conventional explanations. Loeb's approach to this mounting evidence is methodical, building a case through careful mathematical analysis rather than wild speculation. The ecliptic plane alignment represents the first statistical hurdle. Our solar system is relatively flat, with planets orbiting in roughly the same plane like a cosmic dinner plate. This geometric arrangement reflects the rotational collapse of the original nebula that formed our star and planets billions of years ago. Everything that belongs here remembers this fundamental orientation. Interstellar objects shouldn't care about our local geometry. They arrive from other star systems with their own orientations, their own rotational axes, their own histories of formation and ejection. When something enters from interstellar space, it should approach from a random direction at a random inclination angle. The probability that it would align closely with our ecliptic plane is roughly 1 in 500, unlikely but not impossible. Atlas aligns with the ecliptic plane to within 5 degrees. That places it in the narrow band where our planets orbit, arriving as if it understands and respects our solar system's fundamental architecture. For a random interstellar visitor, this represents the first statistical anomaly worth noting. But the planetary encounters transform this curious coincidence into something far more improbable. Atlas doesn't just pass through our solar system at some arbitrary distance from the planets. It passes close to 3 of them, Mars, Venus, and Jupiter, during its flyby. More critically, it arrives at each planet's orbital position when that planet happens to be nearby. Think about what this requires. The planets are constantly moving, following their individual orbital schedules like clockwork. Mars completes its orbit in 687 Earth days. Venus takes 225 days. Jupiter requires nearly 12 Earth years. They're at different distances from the Sun, traveling at different speeds, and they're only in specific locations at specific times. For an interstellar object to encounter all 3 during a single pass through the solar system, the timing must align with extraordinary precision. It's not enough for Atlas's trajectory to cross these orbital paths. It must cross them when the planets are actually present. The 3-dimensional choreography required makes the calculation complex, but the result is clear. The combined probability is approximately 1 in 20,000. 1 in 20,000. We're no longer talking about unlikely coincidences. We're entering the realm of statistical significance, where rational observers begin questioning whether pure chance provides an adequate explanation. And this calculation doesn't include the ecliptic alignment, which represents an independent statistical role. The October 3rd Mars encounter illustrates this precision timing perfectly. Atlas will pass within 29 million kilometers of Mars, close enough that NASA's Mars Reconnaissance Orbiter can photograph it with the HiRISE camera. This isn't just spatial proximity, it's temporal coordination. If Atlas had arrived a few weeks earlier or later, Mars would have been elsewhere in its orbit, and the encounter wouldn't occur. The statistical improbability deepens when you consider the arrival date at perihelion. October 29th represents the moment when Atlas reaches its closest approach to the Sun, but it also represents the moment when Earth will be positioned on the exact opposite side of our star. This geometric alignment creates perfect solar conjunction, complete observational blackout from our planet's perspective. If you randomly vary Atlas's speed by small amounts, shifting its arrival time at perihelion by days or weeks, the probability that Earth would be positioned for perfect solar conjunction drops significantly. The calculation depends on the specific parameters you choose, but Loeb estimates the odds at roughly 1 in 20, another improbable but not impossible coincidence. Now comes the crucial step in statistical analysis, combining independent probabilities. When multiple unlikely events must all occur simultaneously, you multiply their individual probabilities to determine the overall likelihood. The ecliptic alignment 1 in 500, the triple planetary encounter 1 in 20,000, and the solar conjunction timing 1 in 20 combine to create odds of roughly 1 in 200 million. 1 in 200 million. That's the statistical equivalent of winning a major lottery. It can happen, someone does win every lottery eventually, but when it happens you pay attention. You ask questions. You wonder if something beyond pure chance might be involved. But Loeb goes further, adding another layer of improbability to the analysis. The size distribution of interstellar objects should follow established patterns observed throughout the cosmos. Small objects vastly outnumber large ones in every population we've studied, from asteroids to comets to stellar remnants. This scaling law reflects fundamental physics. It's easier to eject small fragments than large masses during planetary formation processes. Based on theoretical models of interstellar object populations, we should discover roughly 100,000 Oumuamua-sized objects before encountering something as massive as Atlas. 100,000 small interstellar visitors should precede each large one, reflecting the natural size distribution created by ejection processes in other planetary systems. Yet, we've only detected 2 confirmed interstellar objects before Atlas, Oumuamua in 2017 and 2I Borisov in 2019. Both were small, both were in the expected size range for early detections. Then Atlas appeared, potentially 1,000 times more massive than its predecessors, arriving third in our sequence of discoveries, rather than 100,000th. This size anomaly adds another statistical layer to Atlas's improbable profile. Not only does its trajectory show multiple unlikely characteristics, but its very existence challenges our understanding of how often large interstellar objects should appear. Each additional anomaly compounds the statistical improbability, pushing the cumulative odds toward levels that demand serious consideration of alternative explanations. The mounting statistical evidence doesn't prove Atlas is technological. Statistics never provide proof, only probabilities, but they do establish a threshold where scientific objectivity requires considering hypotheses that might initially seem unlikely. When the odds against natural explanation reach millions to one, the technological hypothesis begins to merit serious investigation, rather than dismissive rejection. Loeb frames this in terms of scientific methodology. If you observed someone rolling dice and getting double sixes 10 times in a row, you wouldn't immediately conclude the dice were loaded. The odds are roughly 1 in 60 million, unlikely but theoretically possible, but you would examine the dice carefully. You would test them. You would investigate the possibility of manipulation before accepting such an extraordinary streak of luck. Atlas represents astronomy's equivalent of rolling double sixes repeatedly. Each measurement reveals another improbable characteristic. Each calculation pushes the odds further from random chance. Each new observation adds weight to the mounting statistical case for something beyond natural coincidence. October 29th will provide the ultimate statistical test. If Atlas emerges from solar conjunction on an altered trajectory, if it has somehow captured into orbit around our Sun, the statistical argument becomes academic. Natural objects don't execute precision course corrections timed to coincide with observational blind spots. That level of coordination would transform statistical improbability into observational impossibility, finally providing the definitive evidence that would settle the debate about Atlas's true nature once and for all. October 3rd marks more than just another planetary encounter. It represents our first opportunity to see Atlas with unprecedented clarity, stripped of the gas and dust that has obscured its true nature since discovery. When NASA's Mars Reconnaissance Orbiter turns its high-resolution imaging science experiment camera toward our interstellar visitor, we'll get our closest look yet at what might be humanity's first technological artifact from another star system. HiRISE wasn't designed for interstellar object photography. Built to study the Martian surface with extraordinary detail, it can resolve features as small as 1 meter across from its orbital altitude of roughly 300 kilometers above Mars. The camera has been operating since 2006, capturing over 60,000 images of the red planet's surface, revealing everything from seasonal changes to ancient river valleys to the tracks left by rovers exploring the planet below. But on October 3rd, HiRISE will pivot toward a target unlike any it has ever observed. From a distance of 29 million kilometers, closer than any Earth-based telescope can achieve, it will attempt to photograph Atlas during the closest approach to Mars. The resolution won't match surface observations, but it should be sufficient to separate the solid nucleus from the surrounding coma for the first time since Atlas's discovery. This separation between nucleus and coma represents a crucial measurement for understanding Atlas's true nature. Every image we've captured so far shows a fuzzy, comet-like object surrounded by clouds of gas and dust. The brightness we measure, the size estimates we calculate, the spectroscopic signatures we detect, all are contaminated by this surrounding material. We're essentially trying to photograph a light bulb while someone shines a flashlight in our eyes. HiRISE's resolution should cut through this observational fog. At 29 million kilometers distance, the camera's theoretical resolution limit is approximately 150 meters per pixel. That's not enough to see surface details, but it's more than adequate to distinguish between a solid central body and the diffuse material surrounding it. For the first time, we'll see Atlas's actual shape and size rather than the glowing cloud that has defined our observations. The shape analysis could prove decisive in determining Atlas's nature. Natural comets typically display irregular, potato-shaped profiles reflecting their formation through accretional processes and subsequent impacts. They're lumpy, cratered, asymmetric objects that clearly show their chaotic histories. The European Space Agency's Rosetta mission provided spectacular close-up images of Comet 67P Churyumov-Gerasimenko, revealing a highly irregular body that looks exactly like what you'd expect from a natural accumulation of ice and rock. If Atlas shows similar irregularity, if its nucleus appears rough and chaotic like other comets, that would support natural explanations for its unusual characteristics. But if HARIS reveals unexpectedly smooth surfaces, geometric regularity, or artificial-looking features, the technological hypothesis would gain substantial credibility. Advanced manufacturing techniques produce objects with very different visual signatures than natural accretion processes. The size measurement from HiRISE will also resolve one of the key uncertainties in Atlas's profile. Current estimates based on brightness and thermal emission suggest a nucleus diameter between 5 and 20 kilometers, but this range carries enormous implications for the mass budget calculations. A 5-kilometer nucleus massing 33 billion tons would require extraordinary density, denser than most metals. A 20-kilometer nucleus with the same mass would have more reasonable density but would challenge size distribution models for interstellar objects. HiRISE's direct measurement will eliminate this uncertainty. Whatever size the camera reveals will provide a definitive constraint on Atlas's density, internal structure, and formation mechanism. Combined with the mass estimate from trajectory analysis, this will finally allow meaningful comparisons with known comet populations and theoretical models of interstellar object properties. But the October 3rd encounter offers possibilities beyond passive observation. Loeb has speculated that if Atlas is indeed a technological artifact, it might use planetary encounters for reconnaissance purposes. Passing close to Mars provides an ideal opportunity to deploy smaller probes or sensors that could investigate the planet while the main body continues toward perihelion. The physics of such deployment would be straightforward. A small probe ejected from Atlas with a velocity change of just a few kilometers per second could intercept Mars while the parent object continues on its planned trajectory. From Earth's perspective, we would be unlikely to detect such a deployment. Objects smaller than about 100 meters are effectively invisible at interplanetary distances with current telescopes. Mars itself offers an interesting target for potential reconnaissance. As humanity's second home in the solar system, Mars hosts multiple active spacecraft, ongoing terraforming research, and clear evidence of technological activity. Any intelligence interested in assessing human capabilities and expansion plans would find Mars a logical observation target. The constellation of spacecraft around Mars also provides an opportunity for detection that doesn't exist elsewhere in the solar system. In addition to HiRISE on the Mars Reconnaissance Orbiter, the European Space Agency's Mars Express, the Trace Gas Orbiter, and NASA's MAVEN and Odyssey orbiters all maintain active observation schedules. Multiple ground-based rovers could potentially detect atmospheric or electromagnetic anomalies associated with probe deployment. This surveillance network around Mars is far more comprehensive than anything protecting Earth or the other planets. If Atlas does deploy reconnaissance assets, October 3rd provides both the optimal trajectory mechanics and the best chance of detection we're likely to have. The timing of the Mars encounter also fits suspiciously well with Atlas's overall trajectory profile. Rather than a random coincidence, the close approach occurs at precisely the moment when Atlas would have maximum flexibility for course corrections and probe deployment. It happens early enough in the inner solar system approach to allow for reconnaissance data gathering before the critical perihelion decision point on October 29th. From a strategic planning perspective, the Mars flyby represents perfect reconnaissance timing. Any intelligence deployed there would have nearly 4 weeks to assess the target, transmit data back to the main body, and inform decisions about whether to remain in the solar system or continue outward. The orbital mechanics provide exactly the schedule you'd want for comprehensive intelligence gathering before committing to permanent residence. But even if Atlas proves entirely natural, the October 3rd encounter will provide invaluable scientific data about interstellar objects. We'll get our first clear view of a comet nucleus from another star system, allowing direct comparison with comets formed in our own solar neighborhood. The compositional analysis, surface morphology, and structural characteristics will inform models of planetary formation and evolution throughout the galaxy. The images from HiRISE will also establish precedents for observing future interstellar visitors, As the Vera-Rubin Observatory comes online and begins detecting interstellar objects, monthly or even weekly, we'll need efficient methods for characterizing them quickly. The techniques developed for Atlas observation will become standard protocols for evaluating the stream of visitors we expect in the coming years. October 3rd thus represents more than just another observation opportunity. It's our first real chance to see an interstellar visitor clearly, without the obscuring effects of gas and dust that have frustrated analysis since Atlas's discovery. Whether that clear view reveals a natural comet from another star system, or something far more extraordinary, the images captured by HiRISE will fundamentally change our understanding of what's currently racing toward perihelion and the critical decision point that awaits just 26 days later. The chemistry of Atlas tells a story that becomes more puzzling the deeper we dig into the spectroscopic data. What initially appeared to be straightforward cometary composition, water ice, carbon dioxide, simple organic compounds has evolved into a chemical profile that challenges standard models of comet formation and raises intriguing questions about surface modification, interior structure, and the possibility of engineered materials masquerading as natural substances. The James Webb Space Telescope's observations on August 6 provided our most detailed chemical analysis to date, revealing a surface dominated by carbon dioxide ice in proportions unlike anything we've seen in natural comets from our solar system. The CO2-to-water ratio measured at roughly 8:1 places Atlas among the most carbon dioxide-rich objects ever observed, suggesting formation conditions radically different from those that created comets in our local neighborhood. This chemical signature becomes even more intriguing when you consider the implications for Atlas's origin and journey. Carbon dioxide ice is less stable than water ice under most conditions, sublimating at lower temperatures and pressures. For Atlas to retain such high concentrations of CO2 after potentially millions of years of interstellar travel suggests either formation in an extremely cold environment or active preservation mechanisms that prevented loss during transit. The temperature requirements for CO2 stability point toward formation in the outer regions of its home star system, far beyond the equivalent of our Kuiper belt. Such frigid conditions would indeed favor carbon dioxide retention over water ice, but they would also suggest a planetary system with characteristics quite different from our own. Stars with different metallicities, different planetary formation histories, or different evolutionary stages could produce comets with exotic chemical compositions. But there's another interpretation that Loeb finds increasingly compelling as more data accumulates. What if the surface chemistry we're observing doesn't reflect Atlas's true composition? What if the CO2-rich coating represents material acquired during interstellar travel rather than original formation chemistry? Interstellar space isn't empty. It contains diffuse gas clouds with varying chemical compositions, including significant concentrations of carbon dioxide molecules. Any object traveling through these clouds for extended periods would gradually accumulate surface deposits, like a spacecraft collecting micrometeorites and cosmic dust. Over millions of years, this accretion process could build up substantial layers of foreign material. This accretion hypothesis offers an elegant explanation for Atlas's unusual surface chemistry, while opening possibilities for radically different interior composition. If the CO2-rich layer represents interstellar frost accumulated during travel, the object beneath could be made of entirely different materials, perhaps even substances that would clearly indicate technological origin if exposed to direct observation. The masking effect of surface deposits has precedent throughout our solar system. Many asteroids show surface compositions that differ dramatically from their interiors, revealed only when impacts create fresh exposures or when deep drilling samples subsurface materials. For an interstellar traveler, this natural camouflage would be even more pronounced after eons of exposure to varying chemical environments in interstellar space. But the most perplexing aspect of Atlas's chemistry emerged in September, when ground-based observers captured images showing a distinctive green glow during the lunar eclipse. Green coloration in comets typically results from diatomic carbon, C2 molecules excited by solar ultraviolet radiation. When these molecules absorb UV light, they fluoresce at specific wavelengths that produce the characteristic green emission. The puzzle lies in the timing and context of this green glow. Spectroscopic observations from just a month earlier had shown Atlas to be remarkably depleted in carbon chain molecules compared to typical comets. The Kitt-Peak Observatory measurements placed it among the most carbon-deficient comets on record, making the subsequent green coloration unexpected and difficult to explain through conventional outgassing models. Where did the diatomic carbon come from? One possibility involves subsurface chemistry becoming exposed as Atlas approached the Sun and heating intensified. Deeper layers of material, previously frozen and inactive, could contain different chemical compositions than the surface deposits observed earlier. As solar heating penetrated deeper into Atlas's structure, it might have reached carbon-rich layers that began outgassing for the first time. But there's also a more exotic possibility that deserves consideration. The Very Large Telescope in Chile detected dramatic increases in cyanide production from Atlas during late August, with concentrations rising steeply as it approached the Sun. Cyanide compounds can produce greenish coloration under certain conditions, potentially explaining the eclipse observations without requiring massive amounts of diatomic carbon. Cyanide's presence in comets isn't unprecedented. Many natural comets produce detectable quantities as organic molecules break down under solar heating. But the concentration levels observed in Atlas exceed typical values, and the rapid increase suggests either unusually rich organic deposits or chemical processes operating at higher rates than normal comet outgassing models predict. From an engineering perspective, both carbon dioxide and cyanide offer useful properties for technological applications. K2 provides excellent thermal management characteristics, sublimating at predictable temperatures to create cooling effects. It's also relatively inert chemically, making it suitable for protective coatings or thermal barrier applications. Advanced civilizations designing interstellar vehicles might well choose CO2-rich surface materials for their thermal and protective properties. Cyanide compounds, despite their toxicity to Earth-based life, offer interesting possibilities for high-energy chemistry and propulsion applications. They can serve as precursors for more complex chemical reactions, and their breakdown products include both carbon and nitrogen, elements essential for many advanced material synthesis processes. The threshold-like appearance of the green glow adds another layer of intrigue to Atlas's chemical behavior. Rather than gradual development over weeks or months, the coloration appeared suddenly during the eclipse observations, suggesting a rapid onset triggered by specific conditions. This behavior resembles activation more than natural sublimation, which typically produces gradual changes as heating increases. If Atlas incorporates technological systems that respond to temperature or solar radiation thresholds, the green emission could represent operational changes rather than simple outgassing. Systems powering up, chemical processes activating, or internal components beginning operation could all produce byproducts that would appear as increased chemical emissions to our instruments. The spectroscopic data also reveals isotopic ratios that provide clues about Atlas's formation environment and subsequent history. Different star systems produce different isotopic signatures based on their stellar masses, ages, and metallicities. By analyzing the precise isotopic composition of Atlas's emissions, astronomers can potentially determine characteristics of its home system and the processes that led to its ejection into interstellar space. But isotopic analysis becomes more complex. If Atlas's surface chemistry has been modified by interstellar accretion or technological processes, the isotope ratios we measure might reflect the average composition of materials encountered during its journey rather than its original formation chemistry. Distinguishing between these possibilities requires careful analysis of multiple isotopic systems and comparison with theoretical models of interstellar chemical evolution. The October 29th perihelion passage will provide crucial new chemical data as Atlas reaches maximum solar heating. If the unusual chemistry reflects surface coatings or deposits, the intense heating might strip away these layers and expose different materials beneath. Alternatively, if the chemistry reflects technological processes, perihelion might trigger additional activation events that would reveal more about Atlas's true nature. Whatever the chemical analysis ultimately reveals, Atlas's composition already places it outside the normal range of interstellar objects we expected to encounter. Whether this reflects exotic natural formation processes or something more purposeful, the chemistry adds another piece to the puzzle of an object that refuses to fit conventional categories. As we approach the critical decision point of October 29th, these chemical fingerprints will help determine whether we're observing natural processes pushed to their limits, or something altogether different masquerading as a comet from the stars. The timing of solar conjunction represents perhaps the most strategically suspicious aspect of Atlas's entire trajectory profile. If you were an advanced intelligence planning an interstellar reconnaissance mission, the period from October 15th through November 30th would offer the perfect window for unobserved operations in our inner solar system. The Sun itself becomes a shield, blocking Earth's most sophisticated telescopes during the most critical phase of any potential orbital maneuver. Solar conjunction occurs when an object appears to pass behind the Sun as viewed from Earth. The geometric alignment creates a communication and observation blackout that affects everything from Mars missions to deep space probes. NASA routinely suspends commanding of Mars rovers during conjunction periods because the Sun's radio interference makes reliable communication impossible. For optical astronomy, the effect is even more dramatic. Attempting to observe objects near the Sun is like trying to spot a candle flame while staring into a searchlight. For Atlas, conjunction begins in mid-October when it approaches within about 3 degrees of the solar disk as seen from Earth. Ground-based telescopes will lose the ability to track it first, overwhelmed by atmospheric scattering of sunlight during daylight hours and unable to point close enough to the Sun during nighttime observations. Space-based telescopes like Hubble and Webb have even stricter limitations, with protective protocols that prevent pointing within 45 to 85 degrees of the Sun to avoid instrument damage. The duration of this observational blackout extends far beyond the few hours of precise solar alignment. From Earth's perspective, Atlas disappears behind the Sun in mid-October and doesn't re-emerge until late November, more than 6 weeks of complete invisibility during the most crucial period of its solar system encounter. This extended blindness coincides precisely with perihelion passage on October 29th, when any orbital maneuver would be most effective. The strategic implications of this timing are profound. If Atlas possesses propulsion capabilities, the conjunction period offers an unparalleled opportunity for course corrections without human observation. It could fire engines, deploy additional objects, or execute complex maneuvers while remaining completely hidden from our detection systems. We would only discover such activities weeks later when Atlas re-emerges, and we recalculate its trajectory based on its new position. But the sophistication of this timing goes beyond mere coincidence, avoidance. The conjunction period aligns almost perfectly with the optimal window for orbital capture maneuvers. Perihelion represents the point of highest velocity and strongest gravitational influence, exactly when reverse Oberth burns would be most efficient. The fact that this optimal maneuver point occurs during our observational blackout suggests either remarkable luck or deliberate planning. From a tactical perspective, the hidden maneuver window provides multiple strategic advantages. First, it prevents real-time assessment of Atlas's capabilities. We can't observe its propulsion systems, measure thrust levels, or analyze maneuvering techniques while they're operating. This information blackout limits our ability to understand the technology we might be dealing with and handicaps any defensive preparations we might consider necessary. Second, the timing creates uncertainty about Atlas's intentions and future trajectory. During the conjunction period, we can't track its precise movements or predict its post-perihelion path. This uncertainty extends our planning horizon and limits our ability to respond quickly to changed circumstances. By the time we regain visual contact, Atlas could be committed to any number of different trajectories, from immediate departure to permanent capture. Third, the observational gap provides operational security for any reconnaissance activities Atlas might conduct during its closest approach to the inner solar system. Perihelion brings it within 1.4 astronomical units of the Sun, closer to Earth than we've been able to observe it clearly since discovery. If Atlas deploys sensors, probes, or communication equipment during this period, we wouldn't detect the deployment or track the resulting objects until well after the fact. The engineering requirements for such precisely timed trajectory planning are substantial. Atlas would need detailed knowledge of Earth's orbital position, our astronomical capabilities, and the geometric constraints that create conjunction conditions. This implies either extensive prior observation of our solar system or access to theoretical models sophisticated enough to predict conjunction timing from interstellar distances. Such precision planning also suggests mission architecture designed around stealth and reconnaissance objectives rather than casual exploration. Scientific missions typically prioritize observation opportunities and communication windows rather than avoiding them. The fact that Atlas's trajectory maximizes rather than minimizes observational gaps points toward different priorities and objectives. The conjunction timing becomes even more intriguing when considered alongside Atlas's other trajectory anomalies. The ecliptic plane alignment maximizes its time within our planetary system's active zone. The multiple planetary encounters provide reconnaissance opportunities at Mars, Venus, and Jupiter, The perihelion timing places it closest to Earth during our observational blackout. Each element supports extended, unobserved operations within our solar system. Historical analysis of spacecraft mission planning reveals how challenging such trajectory optimization would be even for human missions. NASA's trajectory designers spend years calculating optimal launch windows, gravitational assists, and arrival timing for interplanetary missions. Achieving Atlas's level of geometric precision from interstellar distances would require computational capabilities and predictive models far beyond our current abilities. The operational implications extend beyond the conjunction period itself. Once Atlas re-emerges in late November, we'll have limited time to assess any changes in its behavior or trajectory before it either departs the solar system or settles into permanent orbit. This compressed analysis window creates pressure for rapid decision-making about how to respond to whatever we discover. If Atlas has captured into orbit around the Sun, we'll need to quickly determine its new orbital parameters, assess any ongoing activities, and decide whether to attempt communication or take other responsive actions. The conjunction period's observational gap will have eliminated our best opportunity to witness the transition from transit visitor to permanent resident, leaving us to work backward from incomplete data. The timing also affects international coordination efforts. During the conjunction period, no nation or space agency can claim superior observational access or information advantage. We're all equally blind, which could either promote cooperation through shared uncertainty or create suspicion about hidden capabilities and secret observations. The enforced information blackout levels the playing field in ways that might complicate diplomatic responses. Looking beyond Atlas specifically, the conjunction timing sets precedents for evaluating future interstellar visitors. If optimal maneuver windows consistently coincide with our observational blind spots, it might indicate that trajectory planning incorporates knowledge of our capabilities and limitations. This would transform our approach to interstellar object detection and tracking, requiring development of solar-oriented observation platforms or improved international coordination of tracking responsibilities. The October 29th perihelion passage thus represents more than just Atlas's closest approach to our Sun. It marks the beginning of the most critical information gap in humanity's first potential encounter with interstellar technology. For 6 weeks we'll be flying blind while our visitor potentially makes the most important decisions of its mission. When Atlas re-emerges in late November, we'll finally learn whether that precisely timed observational gap concealed the moment when coincidence transformed into confirmation of intentional design. The strategic perfection of this timing may itself be the strongest evidence yet that Atlas represents something far more sophisticated than a wandering chunk of ice and rock from another star system. If Atlas emerges from solar conjunction in late November on an elliptical orbit around our Sun, humanity will face an unprecedented situation that fundamentally changes our relationship with the cosmos. No longer would we be an isolated civilization wondering about the existence of others. We would have a confirmed neighbor, something that chose to remain in our vicinity for purposes we can only begin to imagine. The immediate scientific implications would be revolutionary. Instead of the brief flyby observations that characterized our encounters with Oumuamua and 2I Borisov, we would have years, possibly decades, to study Atlas in extraordinary detail. Every orbit would bring new opportunities for close observation, spectroscopic analysis, and potential interaction. The scientific return from a permanent interstellar visitor would dwarf anything we could achieve during a few months of flyby observations. Long-term observation would allow us to resolve many of the current uncertainties about Atlas's nature and composition. We could track its rotation period with precision, map its surface features, analyze seasonal changes in outgassing patterns, and potentially detect any artificial structures or activities that brief observations might miss. The accumulated data over multiple orbital periods would provide an unprecedented window into the properties of objects from other star systems. But the implications extend far beyond astronomy. A permanent interstellar visitor would validate the hypothesis that technological civilizations exist elsewhere in the galaxy, and that at least some of them are actively exploring nearby star systems. This confirmation would transform fields ranging from astrobiology to philosophy, providing concrete evidence that intelligence is not unique to Earth. The orbital parameters Atlas establishes would reveal important clues about its objectives and capabilities. A highly elliptical orbit with aphelion beyond Jupiter would suggest a conservative strategy, remaining in the outer solar system most of the time while making periodic approaches to the inner planets for observation or resource assessment. Such an orbit would minimize interaction risks while maximizing long-term surveillance opportunities. Alternatively, a more circular orbit within the inner solar system would indicate bolder intentions, maintaining continuous proximity to Earth and the other terrestrial planets. This positioning would facilitate ongoing reconnaissance, communication attempts, or resource utilization activities. The orbital choice itself would provide our first insight into the strategic thinking behind Atlas's mission. The gravitational effects of planetary encounters during each orbit would also reveal Atlas's mass distribution and internal structure. Close passes by Jupiter or Saturn would create measurable perturbations that could expose density variations inconsistent with natural comet composition. These gravitational signatures might finally resolve questions about whether Atlas is solid, hollow, or contains internal structures that wouldn't occur naturally. Resource utilization represents another significant possibility. If Atlas remains in our solar system, the asteroid belt contains vast quantities of metals, rare earth elements, and other materials valuable for technological applications. The outer planets offer access to hydrogen, helium, and other volatiles. A permanent visitor might begin systematic resource assessment and extraction activities that would be impossible during a brief flyby. Such activities would have profound implications for human space development. If Atlas demonstrates advanced mining, processing, or manufacturing capabilities, it might accelerate our own technological development through observation and analysis. Alternatively, if it begins large-scale resource extraction, we might face competition for materials we hoped to utilize for our own expansion into the solar system. The communication possibilities represent perhaps the most transformative potential outcome. A permanent interstellar visitor would provide ongoing opportunities for contact attempts that don't exist with transient objects. We could transmit increasingly sophisticated messages, watch for responses, and potentially establish meaningful dialogue with whatever intelligence controls Atlas. The protocols for such communication attempts would need careful development. Initial messages should probably be mathematical or scientific in nature, universal concepts that any technological civilization would understand. Prime numbers, physical constants, basic geometric relationships could serve as initial contact languages. More complex communications involving cultural, social, or political concepts would require extensive preparation and international coordination. But communication also carries risks. If Atlas represents reconnaissance for less benevolent purposes, our attempts at contact might reveal capabilities, intentions, or vulnerabilities that could disadvantage humanity. The decision of whether and how to communicate would require unprecedented global coordination and careful consideration of potential consequences. The psychological and cultural impacts of confirmed interstellar intelligence would reshape human civilization in fundamental ways. Religions would need to integrate the reality of non-terrestrial intelligence into their cosmologies. Educational systems would need to prepare students for a universe known to contain other technological species. Political structures would face questions about representation and response to entities that transcend national boundaries. International cooperation would become essential in ways never before required. Atlas would represent a global phenomenon requiring global response capabilities. No single nation could claim sovereignty over interstellar visitors, and effective response would require pooling resources, expertise, and decision-making authority across traditional political boundaries. The technological demonstration effects could accelerate human development dramatically. Observing Atlas's propulsion systems, energy sources, and engineering solutions might provide insights that advance our own capabilities by decades or centuries. Even if direct communication proves impossible, careful observation of a functioning interstellar vehicle could revolutionize human space technology. Economic implications would also be substantial. Confirmation of advanced alien technology would likely trigger massive investments in related research and development. Space agencies would receive unprecedented funding. Private companies would race to develop technologies inspired by Atlas's capabilities. The economic disruption could rival the introduction of the internet or the dawn of the nuclear age. Military considerations would inevitably arise as well. An object capable of interstellar travel and precision orbital maneuvers would possess capabilities far beyond current human military technology. Defense establishments worldwide would need to assess potential threats and develop response capabilities for scenarios never before considered possible. The precedent Atlas establishes would also influence our approach to future interstellar visitors. If one object chooses to remain in our solar system, Others might follow. We could find ourselves hosting multiple interstellar residents, each with different objectives and capabilities. The protocols and institutions we develop for Atlas would become templates for managing an increasingly complex interstellar neighborhood. Scientific research priorities would shift dramatically toward understanding Atlas and preparing for additional visitors. Astronomy would refocus on interstellar object detection and characterization. Physics and engineering would prioritize technologies relevant to interstellar communication and potential interaction. Biology and anthropology would explore implications for life and intelligence throughout the galaxy. The time frame for these transformations would depend partly on Atlas's behavior after orbital capture. If it remains passive, simply orbiting without obvious activity, the changes might develop gradually over years or decades. But if it begins active operations, communication attempts, resource utilization, or deployment of additional objects, the pace of change could accelerate dramatically. Perhaps most significantly, Atlas's permanent presence would serve as a constant reminder that Earth is not isolated in the cosmos. Future generations would grow up knowing that intelligence exists elsewhere in the galaxy and that at least some of it takes active interest in other star systems. This awareness would fundamentally alter humanity's perspective on its place in the universe and its responsibilities as a technological civilization. The decision Atlas makes on October 29th to stay or to leave thus carries implications far beyond astronomy. If it chooses to remain, it transforms human civilization's trajectory in ways we can barely begin to imagine. The next few weeks will determine whether humanity enters a new era of cosmic citizenship or continues its solitary development in an apparently empty galaxy. The possibility that Atlas represents a reconnaissance mission designed to assess Earth's technological development and strategic capabilities adds a sobering dimension to its already complex profile. If the anomalies we've documented reflect intentional design rather than natural coincidence, then Atlas's behavior patterns begin to resemble those of an intelligence-gathering operation rather than casual exploration. Consider the trajectory from a surveillance perspective. Atlas approaches our solar system along the ecliptic plane, maximizing its time within the zone where planets orbit and where technological activity would be most concentrated. It makes close passes by 3 different worlds: Mars, Venus, and Jupiter, each offering unique intelligence value for assessing human capabilities and expansion plans. Mars represents humanity's primary extraterrestrial foothold, hosting multiple active spacecraft, ongoing scientific missions, and clear evidence of terraforming research. Any intelligence interested in understanding human space capabilities would find Mars an obvious surveillance target. The October 3rd flyby provides optimal positioning for assessing our planetary exploration infrastructure, technological sophistication, and expansion timeline. Venus, despite its hostile surface conditions, remains a target of significant scientific interest and potential future terraforming efforts. Jupiter's system contains some of the most promising locations for resource extraction and settlement in the outer solar system. A reconnaissance mission would logically want to assess human activities and intentions regarding both locations. The timing of these encounters maximizes intelligence gathering opportunities while minimizing detection risks. Each planetary approach occurs when Atlas's own activity would be partially masked by legitimate astronomical interest in the flyby itself. Scientists focusing on photographing and analyzing Atlas during these encounters would be less likely to notice subtle reconnaissance activities or probe deployments. The orbital mechanics also support extended surveillance capabilities. If Atlas captures into a permanent orbit around the Sun, it would establish a persistent observation platform capable of monitoring Earth's technological development over years or decades. Unlike brief flyby missions that provide only snapshot assessments, permanent residence would enable longitudinal analysis of human capabilities and intentions. From this platform, Atlas could monitor our radio communications, analyze our spacecraft launches, track our industrial development, and assess our military capabilities. Modern Earth generates electromagnetic signatures detectable across interstellar distances, television broadcasts, radar emissions, satellite communications. A sophisticated intelligence-gathering system could learn enormous amounts about human civilization through passive monitoring of these signals. The strategic positioning available through various orbital configurations would provide different surveillance advantages. A highly elliptical orbit would bring Atlas close to Earth periodically for detailed observations while keeping it safely distant most of the time. A more circular orbit would provide continuous monitoring capabilities, but greater exposure to human detection and potential interference. The technological requirements for effective surveillance operations align with the capabilities Atlas appears to possess. Its massive size could accommodate extensive sensor arrays, signal processing equipment, and communication systems needed for comprehensive intelligence gathering. The apparent resistance to trajectory perturbations suggests propulsion capabilities that could support precise positioning for optimal observation geometry. The October 29th timing for potential orbital insertion becomes even more significant when viewed through a surveillance lens. By making its commitment decision during solar conjunction, Atlas would prevent real-time human observation of the transition from transient visitor to permanent resident. This operational security measure would deny us information about its capabilities while ensuring successful establishment of a surveillance platform. But surveillance raises uncomfortable questions about intent and ultimate objectives. Intelligence gathering typically serves specific purposes: threat assessment, resource evaluation, invasion preparation, or strategic planning. The information Atlas might collect during extended surveillance operations could serve benevolent scientific purposes or more troubling strategic objectives. If Atlas represents advanced reconnaissance for a larger exploration effort, the intelligence it gathers could inform decisions about formal contact, resource sharing, or collaborative scientific endeavors. Such missions might precede diplomatic overtures designed to establish peaceful relationships between civilizations separated by interstellar distances. Alternatively, the surveillance could serve threat assessment purposes, determining whether humanity represents a potential danger to other civilizations as our technology advances and our influence expands beyond Earth. Our rapid technological development, demonstrated nuclear capabilities, and aggressive expansion patterns might concern older, more established civilizations monitoring our progress. The darker possibilities involve reconnaissance for hostile purposes. Military strategists throughout history have emphasized the importance of intelligence gathering before major operations. If Atlas represents advanced reconnaissance for less benevolent objectives, the intelligence it collects could inform strategies for neutralizing human civilization before it becomes capable of interstellar expansion. The surveillance hypothesis also explains some of Atlas's more puzzling characteristics. Its unusual chemical composition could reflect materials chosen for stealth properties rather than natural formation processes. The sudden appearance of green coloration might indicate activation of observation systems rather than simple outgassing. The resistance to trajectory perturbations could reflect active station keeping for optimal surveillance positioning. Detection of surveillance activities would require different observational strategies than those used for studying natural comets. Instead of focusing on composition and structure, we would need to monitor for electromagnetic emissions, unusual thermal signatures, or deployment of smaller reconnaissance objects that might be difficult to detect individually. The network of spacecraft around Mars provides one of the few opportunities for detecting such activities. Mars orbiters carry instruments capable of detecting electromagnetic anomalies, unusual particle emissions, or small objects that might be deployed during the October 3rd encounter. If Atlas is conducting surveillance operations, this encounter offers our best chance of catching it in the act. But the surveillance hypothesis also highlights our defensive limitations. If Atlas possesses advanced intelligence gathering capabilities, there's little we could do to prevent ongoing reconnaissance activities. Our ability to detect such operations depends on Atlas making mistakes or using technologies we understand well enough to recognize. The ethical implications of confirmed surveillance would be profound. Unauthorized intelligence gathering by foreign powers is considered an act of espionage under international law, but these frameworks assume human actors operating within terrestrial political boundaries. How would such concepts apply to extraterrestrial reconnaissance operations? The response options would be limited and potentially dangerous. Attempting to interfere with Atlas's operations could provoke retaliation from capabilities we don't understand. But allowing unrestricted surveillance might compromise human security and strategic interests in ways we're only beginning to contemplate. International cooperation would become essential for any effective response to surveillance activities. No single nation possesses the resources or authority to address interstellar reconnaissance operations independently. Developing coordinated response capabilities would require unprecedented levels of global coordination and shared decision-making authority. The precedent established by Atlas's surveillance activities would also influence our approach to future interstellar visitors. If we confirm that at least some interstellar objects conduct intelligence-gathering operations, we would need to develop detection and response protocols for an entire class of potential reconnaissance missions. The technological implications could accelerate human development in unexpected directions. Attempting to counter advanced surveillance capabilities might drive innovations in stealth technology, electromagnetic shielding, or detection systems. The challenge of maintaining operational security against potentially superior intelligence-gathering technologies could stimulate rapid advancement in multiple fields. But perhaps most significantly, confirmed surveillance would fundamentally alter humanity's sense of privacy and security in the cosmos. The knowledge that advanced civilizations might be monitoring our development, assessing our capabilities, and potentially planning responses to our activities would create psychological pressures unlike anything in human history. October 29th thus represents more than just a potential orbital insertion maneuver. If Atlas is indeed conducting surveillance operations, it marks the moment when passive observation might transition to active intelligence gathering from a permanent orbital platform. The implications of this possibility demand serious consideration even if the probability remains uncertain, because the consequences of being wrong about Atlas's intentions could prove catastrophic for human civilization's long-term security and independence. The greatest challenge in evaluating Atlas's true nature lies not in what we can observe, but in recognizing the limitations of our observational capabilities when confronted with potentially advanced technology. Our instruments and analysis methods are calibrated for natural phenomena, optimized for detecting the signatures we expect from comets, asteroids, and other conventional objects. But technology sufficiently advanced to enable interstellar travel might operate using principles and produce signatures entirely outside our current detection paradigms. Consider propulsion systems as the most obvious example. Our experience with spacecraft propulsion is limited to chemical rockets, ion drives, and theoretical concepts like nuclear pulse propulsion or fusion ramjets. We know what these systems look like operationally: bright exhaust plumes, characteristic electromagnetic emissions, thermal signatures detectable across vast distances. We've designed our observation protocols to recognize these familiar patterns, but a civilization capable of interstellar travel would almost certainly use propulsion technologies far beyond our current understanding. Antimatter drives would produce entirely different signature patterns. Field manipulation systems might operate without any visible exhaust. Quantum vacuum energy extraction could power spacecraft through mechanisms we haven't even theorized yet. Our instruments might completely miss propulsion systems operating on principles we haven't discovered. The mass and energy requirements for interstellar travel demand efficiency levels far exceeding anything achieved by human technology. Chemical rockets, our most mature propulsion technology, can barely escape Earth's gravity well. Ion drives achieve higher efficiency but require enormous amounts of time to build significant velocity. Neither approach would be practical for journeys across light-years of space. Advanced propulsion systems would need to achieve specific impulse values orders of magnitude higher than current technology, while maintaining reasonable power-to-weight ratios. The engineering solutions might involve exotic matter states, manipulation of space-time geometry, or energy extraction from vacuum fluctuations. These approaches could operate without producing any signatures. Our current instruments would recognize as artificial. Atlas's apparent resistance to trajectory perturbations from outgassing provides a perfect example of this detection challenge. We can measure the absence of expected non-gravitational acceleration, but we cannot directly detect the mechanisms that might be causing this behavior. If Atlas uses subtle thrust vectoring to counteract outgassing effects, if it employs magnetic field manipulation to control gas emissions, or if it generates propulsive forces through principles we don't understand, these activities would remain invisible to our current observation methods. Energy sources present similar detection challenges. Interstellar missions would require power systems capable of operating reliably for millions of years, while providing enough energy for propulsion, life support, communication, and operations upon arrival. Nuclear reactors might last decades, but not millennia. Solar panels become useless in interstellar space. Radioisotope, thermoelectric generators have limited lifespans and relatively low power output. Advanced civilizations might employ fusion reactors, matter-antimatter annihilation, or even more exotic energy sources we haven't conceived. These systems could operate at efficiency levels and with thermal management techniques that minimize detectable emissions. A sufficiently advanced power system might appear completely cold to our infrared telescopes, while generating tremendous internal energy. The October 29th's observational gap compounds these detection limitations during the most critical phase of Atlas's solar system encounter. If Atlas possesses advanced propulsion systems, the perihelion period when they would be most likely to operate coincides precisely with our inability to observe their operation. We're essentially being denied the opportunity to witness whatever technology might be employed during the most important moment of the entire encounter. Communication systems present another category of technological signatures we might completely miss. Human radio communication uses specific frequency ranges and modulation techniques, optimized for our technology in atmospheric conditions. An interstellar civilization might communicate using neutrino beams, gravitational wave modulation, quantum entanglement effects, or other methods that wouldn't register on any of our current detection systems. Atlas could be transmitting detailed reports of its observations back to its origin civilization without producing any signatures we would recognize as artificial. The James Webb Space Telescope and other advanced observatories are incredibly sensitive to electromagnetic radiation, but only within the wavelength ranges they were designed to detect. Communication methods operating outside these ranges would remain completely invisible to our most sophisticated instruments. Material science limitations also affect our ability to recognize artificial structures. We assume that spacecraft should be made of metals, ceramics, or composites similar to materials we use for our own space vehicles. But advanced civilizations might employ metamaterials with properties unlike anything in nature. Materials that could mimic natural rock and ice while providing structural capabilities far exceeding natural substances. Surface coatings designed to regulate temperature, provide radiation shielding, or create camouflage effects could completely mask underlying technological structures. If Atlas's exterior consists of accumulated interstellar material deposited over millions of years of travel, any artificial structures beneath would be invisible to spectroscopic analysis focused on surface composition. The thermal management requirements for interstellar travel also suggest technologies that might evade our detection methods. Objects traveling through space for geological time periods must protect themselves from radiation, micrometeoroids, and extreme temperature variations. The engineering solutions might involve active thermal control systems that maintain specific temperature profiles regardless of solar heating. Such systems could explain Atlas's unusual outgassing patterns, its resistance to trajectory perturbations, and its apparently arbitrary surface chemistry. Instead of passive responses to solar heating, these characteristics might reflect active thermal management designed to maintain optimal operating conditions for internal systems. Information processing and artificial intelligence capabilities present perhaps the greatest detection challenges. Any technological artifact capable of autonomous interstellar travel would require computational abilities far exceeding current human achievements. These systems might process vast amounts of sensory data, make complex navigational decisions, and adapt their behavior based on encountered conditions. But advanced artificial intelligence might operate using computational principles completely foreign to our digital electronics paradigm. Quantum computers, biological neural networks, or even more exotic information processing systems could function without producing any electromagnetic signatures we would associate with computational activity. The October 29th decision point exemplifies this detection challenge perfectly. If Atlas possesses artificial intelligence systems capable of analyzing the solar system environment and deciding whether to remain or continue outward, this decision-making process could occur entirely without detectable signatures. We might witness the results of sophisticated analysis and planning without recognizing that such activities occurred. The philosophical implications extend beyond mere technical limitations. Clarke's observation that sufficiently advanced technology becomes indistinguishable from magic applies directly to the Atlas evaluation challenge. If we encounter technology centuries or millennia beyond our current capabilities, we might not recognize it as artificial even when observing it directly. This recognition gap creates a profound bias in our analysis methods. We can reasonably evaluate whether Atlas behaves like natural comets we understand, but we cannot meaningfully assess whether it behaves like artificial objects we cannot imagine. The absence of familiar technological signatures doesn't prove natural origin. It might simply reflect technological advancement beyond our conceptual horizons. The solution requires expanding our observation strategies beyond conventional approaches. Instead of looking only for signatures we expect from artificial objects, we need to identify patterns of behavior that would be unlikely in natural objects, regardless of the mechanisms involved. Precise trajectory control, complex timing coordination, and adaptive responses to environmental conditions might indicate intelligence even when the implementing technologies remain invisible. October 29th will test these expanded observation strategies under the most challenging conditions possible. If Atlas employs advanced technologies during its perihelion passage, we may never detect their operation directly. But if it emerges from solar conjunction with altered trajectory, evidence of complex maneuvering, or other signs of directed behavior, we'll know that something beyond our current understanding of natural processes occurred behind the sun's protective shield. The lack of established protocols for handling potentially technological interstellar visitors represents one of the most glaring oversights in humanity's preparation for cosmic encounters. While we have elaborate frameworks for asteroid impact threats, elaborate procedures for first radio contact with extraterrestrial intelligence, and detailed plans for pandemic response, we have no international consensus on how to handle an artifact from another star system that might be actively assessing our civilization. This institutional gap becomes more troubling when you consider the stakes involved. If Atlas represents humanity's first contact with extraterrestrial technology, the decisions made in the coming weeks could establish precedents that influence interstellar relations for generations. Yet we approach this possibility with no coordinated international response capability, no clear decision-making authority, and no agreed-upon principles for managing such encounters. The United Nations Office for Outer Space Affairs oversees international cooperation in space activities, but its mandate focuses primarily on preventing conflicts over terrestrial space assets and coordinating satellite operations. The Committee on the Peaceful Uses of Outer Space addresses some aspects of planetary defense, particularly asteroid impact mitigation, but interstellar visitors fall outside established frameworks designed for objects originating within our solar system. NASA's Planetary Defense Coordination Office represents the most relevant existing institution, tasked with detecting and characterizing potentially hazardous near-Earth objects, but their mandate explicitly focuses on impact threats rather than potential intelligence encounters. The techniques and resources needed to assess whether an object is technological differ fundamentally from those used to calculate collision probabilities and deflection strategies. The SETI Institute and similar organizations have developed protocols for responding to radio signals from extraterrestrial civilizations, but these frameworks assume communication across interstellar distances with entities that remain safely remote. An interstellar visitor actually present in our solar system creates immediate proximity that existing SETI protocols never anticipated. International coordination becomes essential, because no single nation possesses the resources or authority to address interstellar encounters comprehensively. The United States operates some of the world's most advanced space surveillance systems, but comprehensive tracking requires global telescope networks spanning multiple continents. Russia's deep space monitoring capabilities complement Western systems. China's growing space surveillance infrastructure adds crucial coverage in regions other networks might miss. European Space Agency assets, including the Mars orbiters that will observe Atlas during the October 3rd encounter, provide unique observation opportunities unavailable to any single national program. Japanese and Indian space agencies contribute additional monitoring capabilities and expertise. Effective Atlas observation requires coordinating all these assets under some form of unified command structure that doesn't currently exist. The communication challenges extend beyond mere technical coordination. If Atlas proves technological and demonstrates communication capabilities, which organization speaks for humanity? The United Nations provides the most legitimate international forum, but it has no established procedures for extraterrestrial contact scenarios. Individual space agencies lack global authority for such momentous decisions. The timeframe constraints make institutional improvisation particularly challenging. Atlas approaches its critical October 29th decision point in less than 4 weeks. Even if world leaders recognize the urgency and initiated coordination efforts immediately, establishing effective international response mechanisms would require months or years of negotiation, planning, and resource allocation. Military implications further complicate international coordination requirements. If Atlas possesses advanced propulsion capabilities, if it can deploy additional objects or execute precision maneuvers, it represents technology far beyond current human military systems. Defense establishments worldwide would need to assess potential threats and develop response capabilities for scenarios never before considered possible. But military involvement in interstellar contact scenarios carries its own risks. Approaching potentially friendly extraterrestrial technology with military suspicion could provoke hostile responses from beings whose intentions might otherwise be benevolent. The challenge lies in maintaining appropriate caution while avoiding actions that could be interpreted as aggressive or threatening. Economic coordination presents another layer of international response challenges. Confirmation of advanced alien technology would likely trigger massive economic disruption as markets attempt to price in implications for human technology development, resource availability, and geopolitical stability. Managing this disruption would require unprecedented international economic cooperation. The information sharing requirements also challenge existing intelligence and security frameworks. Critical observations about Atlas's capabilities and behavior would need to be shared internationally to enable effective response planning, but such sharing conflicts with national security practices designed to protect sensitive technological information from foreign competitors. Cultural and religious considerations add further complexity to international coordination requirements. Different societies would interpret contact with extraterrestrial intelligence through vastly different cultural and religious frameworks. Building international consensus on appropriate responses would require navigating these diverse perspectives while maintaining unified action capabilities. The precedent establishment aspects make current coordination failures particularly concerning. However humanity responds to Atlas will establish templates for dealing with future interstellar visitors. If we handle this encounter through uncoordinated national responses driven by individual interests rather than collective humanity, we create precedents that could handicap responses to potentially more significant future encounters. Legal frameworks present additional challenges requiring international coordination. Existing space law governs activities within our solar system by terrestrial entities, but it provides no guidance for dealing with extraterrestrial visitors. Questions of sovereignty, property rights, and jurisdiction become meaningless when dealing with entities that predate human legal systems by potentially millions of years. The technological assessment requirements also demand international cooperation. Properly evaluating Atlas's capabilities requires expertise distributed across multiple institutions and nations. Astronomical observation expertise, propulsion engineering knowledge, artificial intelligence analysis capabilities, and strategic assessment skills exist in different organizations worldwide. Resource allocation for intensive Atlas monitoring would strain any single national budget, but becomes manageable through international cost-sharing arrangements. The extended observation campaign needed to properly characterize a potential technological visitor would require telescope time, spacecraft operations, analysis resources, and expert personnel at levels beyond any single space agency's capabilities. The October 29th deadline creates particular urgency for establishing at least provisional coordination mechanisms. Even if comprehensive international frameworks require years to develop properly, the critical observation period during Atlas's solar conjunction demands immediate coordination of existing surveillance assets. The communication protocol development also requires international input. If Atlas demonstrates communication capabilities, the initial messages transmitted could establish the tone for all subsequent interstellar relations. These messages should represent humanity collectively rather than individual nations or organizations, requiring unprecedented international cooperation in their development and transmission. Perhaps most importantly, the Atlas encounter demonstrates the need for permanent international institutions capable of handling interstellar contact scenarios. The Vera Rubin Observatory will soon begin detecting interstellar objects monthly or even weekly. We cannot afford to approach each encounter through improvised coordination mechanisms developed under crisis conditions. The window for establishing effective international response capabilities is closing rapidly. October 29th approaches, whether we're prepared or not. If Atlas emerges from solar conjunction with altered trajectory, indicating technological capabilities, humanity will face its first confirmed interstellar intelligence encounter with whatever coordination mechanisms we can assemble in the next few weeks. The adequacy of these improvised arrangements could determine whether first contact proceeds through rational cooperation or dangerous competition between nations, unprepared for the challenge of cosmic citizenship. Late November and early December represent the most consequential period in human history since the invention of agriculture. The weeks when we'll finally learn whether humanity has gained its first confirmed interstellar neighbor or watched another mysterious visitor disappear into the cosmic void. The data that emerges when Atlas re-emerges from solar conjunction will answer questions that have been building for months, while simultaneously raising new ones that could reshape our understanding of our place in the universe. The timeline for these revelations follows the predictable mechanics of orbital geometry combined with the unpredictable possibilities of technological intervention. Atlas will remain hidden behind the sun's glare until approximately November 25th, when it should become visible to powerful telescopes equipped with coronagraphic capabilities. Ground-based observatories will regain visual contact a few days later, as the angular separation from the sun increases beyond their operational limits. The first measurements will focus on trajectory analysis, comparing Atlas's actual position with predictions based on its pre-conjunction orbit. If Atlas emerges on the same hyperbolic trajectory it entered with, the natural comet explanation gains substantial support. The perihelion passage would have been a brief encounter with intense solar heating, followed by a return to the cold darkness of interstellar space. Another curious visitor catalogued and filed away. But if Atlas appears in a different location than predictions indicate, if its velocity has changed or its trajectory has shifted, we'll know immediately that something extraordinary occurred during the hidden weeks behind the sun. The magnitude and direction of any trajectory changes will reveal the nature and purpose of whatever intervention took place during the observational blackout. The mathematical analysis required to detect and characterize trajectory changes demands extraordinary precision. Atlas's position must be measured to within hundreds of kilometers across distances of hundreds of millions of kilometers. Its velocity changes must be detected at the level of meters per second when the object is traveling at dozens of kilometers per second. These measurements push our astrometric capabilities to their absolute limits. Fortunately, the global network of astronomical facilities provides the precision needed for such measurements. The combination of ground-based telescopes, space-based observatories, and radar systems operated by multiple nations can determine Atlas's post-conjunction trajectory with unprecedented accuracy. Within days of regaining visual contact, we'll know definitively whether its orbit has changed. The European Space Agency's JUICE spacecraft will play a crucial role in these revelations. Currently en route to Jupiter but still relatively close to the Sun, JUICE possesses multiple instruments capable of characterizing Atlas during its post-conjunction emergence. The spacecraft's position provides observation angles unavailable from Earth-based systems, enabling three-dimensional trajectory analysis that single-point observations cannot achieve. JUICE's measurements will arrive with significant delay due to communication travel time and data transmission limitations, but they will provide independent verification of Earth-based observations. If both Earth and JUICE detect the same trajectory changes, the reliability of orbital alteration measurements becomes virtually unquestionable. The spectroscopic analysis during December encounters will reveal whether Atlas's chemical behavior has changed during its perihelion passage. If it's truly a natural comet, the intense solar heating should have triggered predictable changes in outgassing patterns, surface composition, and volatile depletion. Comparing pre- and post-conjunction spectra will show whether these expected changes occurred or whether Atlas's chemistry reflects other processes. But the most significant revelations may come from behavioral analysis, rather than positional measurements. If Atlas has captured into orbit around our Sun, its new trajectory will reveal intended orbital parameters that provide clues about long-term objectives. A highly elliptical orbit, keeping it primarily in the outer solar system, would suggest cautious long-term observation strategies. A more circular orbit within the inner solar system would indicate bolder intentions involving closer proximity to Earth and the other terrestrial planets. The close approach to Earth, scheduled for mid-December, provides unprecedented observation opportunities regardless of Atlas's orbital status. At minimum distance of approximately 1.8 astronomical units, our most powerful telescopes will achieve resolution capabilities impossible during earlier observations. The Hubble Space Telescope, James Webb Space Telescope, and ground-based adaptive optics systems will all focus on Atlas simultaneously. These observations will finally resolve questions about Atlas's size, shape, and surface characteristics that have persisted since discovery. If it's a natural comet, we should see irregular morphology consistent with gravitational accretion and impact history. If it's something else, geometric regularity, or obviously artificial features might finally provide unambiguous evidence of technological origin. The December timeframe also coincides with planned observations by NASA's Juno spacecraft currently orbiting Jupiter. While Juno won't achieve the close approach distances possible from Earth-based systems, its instruments are specifically designed for detailed analysis of space objects. The spacecraft's magnetometer, particle detectors, and imaging systems could reveal electromagnetic signatures or other characteristics invisible to purely optical observations. International coordination of December observations will test humanity's ability to cooperate in analyzing potentially transformative discoveries. If ATLAS proves technological, the data collected during December will inform decisions about communication attempts, defensive preparations, and long-term response strategies. Sharing this information across national boundaries and institutional boundaries becomes essential for effective analysis. The public communication challenges during December will be immense regardless of what the observations reveal. If ATLAS proves natural, managing public disappointment and maintaining interest in continued interstellar object research will require careful messaging. If it proves technological, managing public excitement, fear, and speculation will demand unprecedented coordination between scientific institutions, government agencies, and media organizations. The December revelations will also establish precedents for handling future interstellar visitors. The Vera Rubin Observatory's systematic sky survey will begin detecting similar objects regularly, potentially monthly or even weekly. The protocols, institutions, and international agreements developed for ATLAS analysis will become templates for managing an increasingly busy schedule of interstellar encounters. But perhaps most significantly, December will determine whether humanity enters the new year as a civilization that has confirmed the existence of extraterrestrial intelligence, or one that continues to wonder about its cosmic solitude. The psychological, cultural, and philosophical implications of this distinction will influence human development for generations regardless of what specific discoveries emerge from the ATLAS encounter. The data analysis during December will also inform theoretical models of interstellar object populations, planetary formation processes in other star systems, and the likelihood of technological artifacts among the objects we detect. Each measurement adds to our understanding of the galaxy's structure and the prevalence of intelligence throughout cosmic history. As we approach this revelation timeline, the anticipation builds toward answers that have been months in the making. October 29th represents the moment when ATLAS makes its critical decision, but December represents the moment when humanity learns what that decision was and begins grappling with the implications for our species' future in a universe that may prove far more populated and far more interesting than we ever dared imagine. If ATLAS proves technological and establishes permanent residence in our solar system, it will trigger a cascade of scientific and institutional changes that fundamentally transform humanity's approach to cosmic exploration and interstellar relations. The confirmation that advanced technology can and does traverse the gulf between stars will revolutionize fields ranging from astronomy to astrobiology, while creating urgent demands for new institutions and capabilities we've never needed before. The immediate impact on astronomical observation priorities will be profound and permanent. Every major telescope, every space-based observatory, every radar system capable of tracking distant objects will suddenly refocus on interstellar visitor detection and characterization. The techniques developed for ATLAS analysis will become standard protocols applied to every anomalous object detected in our solar system. The Vera Rubin Observatory's systematic sky survey will transform from a general astronomical research program into humanity's primary early warning system for technological visitors. Currently designed to catalogue asteroids, comets, and transient phenomena, Rubin will add sophisticated algorithms, specifically designed to identify objects with trajectory, timing, or behavioral characteristics suggesting artificial origin. This observational revolution will require unprecedented international coordination. No single nation possesses sufficient telescope resources to monitor the entire sky continuously with the resolution and sensitivity needed to detect subtle technological signatures. The global network of astronomical facilities will need integration under coordinated command structures that don't currently exist. The technological implications extend far beyond astronomy. Confirmation that interstellar travel is achievable will accelerate human research into advanced propulsion systems, exotic energy sources, and the engineering challenges of building vehicles capable of surviving million-year journeys across interstellar distances. Universities will establish new interdisciplinary programs combining physics, engineering, and astrobiology, Private industry will respond with massive investments in related technologies. Companies will race to develop propulsion systems inspired by observations of Atlas's capabilities. Material science research will focus on substances capable of withstanding interstellar radiation, micrometeorite bombardment, and extreme temperature variations. The economic impact could rival the introduction of the internet or the beginning of the space age. The artificial intelligence implications deserve particular attention. Any object capable of autonomous interstellar navigation must possess computational capabilities far exceeding current human achievements. These systems would need to process vast amounts of sensory data, make complex navigational decisions, and adapt their behavior based on encountered conditions throughout journeys potentially lasting millions of years. Studying Atlas's artificial intelligence systems, even from a distance, could provide insights that advance human computational capabilities by decades or centuries. Machine learning algorithms, autonomous decision-making systems, and long-term goal optimization techniques, demonstrated by interstellar technology, could revolutionize terrestrial applications from autonomous vehicles to medical diagnosis systems. The search for extraterrestrial intelligence will undergo fundamental transformation. SETI programs currently focus on detecting radio signals from distant civilizations, assuming that first contact will occur through electromagnetic communication across interstellar distances. Atlas demonstrates that technological civilizations send physical emissaries rather than just messages. This revelation will shift SET priorities toward detecting and characterizing interstellar visitors rather than listening for distant radio transmissions. The technical requirements differ dramatically. Optical telescopes and trajectory analysis replace radio dishes and signal processing. The institutional frameworks designed for Radio City will need complete restructuring. International law and governance structures will face unprecedented challenges requiring rapid institutional innovation. Existing space law governs activities within our solar system by terrestrial entities, but provides no framework for regulating interactions with extraterrestrial technology. New treaties, agreements, and institutions will need development with unprecedented urgency. The United Nations will likely establish new offices or expand existing agencies to handle interstellar contact scenarios. The Committee on the Peaceful Uses of Outer Space will require mandate expansion and resource increases. Entirely new international organizations may emerge specifically focused on managing humanity's relationship with confirmed extraterrestrial intelligence. Military implications will drive parallel institutional changes. Defense establishments worldwide will need to assess potential threats and develop response capabilities for scenarios involving technology far beyond current human achievements. This will require new forms of international military cooperation and coordination previously considered unnecessary. The educational implications will reshape curricula from elementary through graduate levels. Students will grow up knowing that intelligence exists elsewhere in the galaxy, and that at least some of it takes active interest in other star systems. Astronomy, physics, engineering, and biology programs will need significant modification to address confirmed extraterrestrial intelligence. Cultural and religious institutions will face the challenge of integrating confirmed alien intelligence into existing belief systems and worldviews. Some religious frameworks will adapt relatively easily, while others may require fundamental re-examination of core doctrines about humanity's place in creation and cosmic purpose. The psychological implications for human civilization deserve careful consideration. Confirmation that advanced civilizations exist and actively explore nearby star systems will fundamentally alter humanity's sense of cosmic significance and security. Some individuals will find this confirmation thrilling and inspiring. Others may experience anxiety or existential concerns about human relevance in a galaxy populated by superior intelligences. Public communication strategies will require unprecedented coordination between scientific institutions, government agencies, and media organizations. Managing public understanding of confirmed extraterrestrial intelligence while preventing panic, unrealistic expectations, or dangerous speculation will demand carefully orchestrated information campaigns. The research priority shifts will affect university programs, government funding allocations, and private research investments across multiple fields. Astrobiology will expand dramatically as the likelihood of life elsewhere becomes confirmed fact rather than hopeful speculation. Planetary science will refocus on understanding worlds that might host or have hosted technological civilizations. The timeline for these cascading changes will depend partly on Atlas's specific behavior and capabilities. If it remains largely passive, the transformation might occur gradually over years. But if it demonstrates active communication capabilities, resource utilization activities, or deployment of additional objects, the pace of change could accelerate dramatically. Perhaps most significantly, Atlas's permanent presence will establish precedents and expectations for future interstellar encounters. The institutions, protocols, and international agreements developed for managing humanity's first confirmed technological visitor will become templates for handling potentially numerous subsequent encounters, as our detection capabilities improve and the frequency of discoveries increases. The cascade of discoveries triggered by Atlas's technological confirmation will thus extend far beyond the object itself. It will fundamentally restructure human civilization's approach to cosmic exploration, international cooperation, and our species' long-term development as a potentially spacefaring civilization, in a galaxy we now know contains other intelligence actively exploring the cosmos. The possibility that Atlas might establish communication capabilities once permanently positioned in our solar system raises profound questions about humanity's readiness for interstellar dialogue. Unlike the abstract scenarios explored by SETI researchers for decades, potential communication with Atlas would involve direct, real-time exchange with a technological intelligence actually present in our cosmic neighborhood. The preparation requirements extend far beyond developing transmission protocols to encompass fundamental questions about who speaks for humanity and what messages we should send. The technical aspects of interstellar communication present formidable challenges even when both parties occupy the same star system. Radio transmissions represent the most obvious communication medium, but Atlas's advanced technology might utilize entirely different methods: neutrino beams, gravitational wave modulation, quantum entanglement effects, or techniques we haven't discovered. Our communication attempts must begin with methods we understand while remaining alert for response patterns we might not immediately recognize. Mathematical concepts offer the most promising foundation for initial contact attempts. Prime numbers, physical constants, geometric relationships, and basic arithmetic represent universal concepts that any technological civilization must understand, regardless of their biological origins or cultural development. These mathematical languages provide common ground for establishing basic communication protocols before attempting more complex exchanges. The Arecibo message transmitted in 1974 provides a template for mathematical communication approaches, though Atlas's proximity would allow much more sophisticated exchanges than the simple pictographic message sent toward the globular cluster, M13. We could transmit increasingly complex mathematical relationships, scientific data about our solar system, and eventually more abstract concepts about human civilization and Earth's biosphere. But the institutional questions surrounding communication attempts prove far more challenging than the technical aspects. Who has the authority to speak for humanity in potential exchanges with extraterrestrial intelligence? The United Nations provides the most obvious international forum, but it has no established procedures for extraterrestrial contact scenarios and no technical capabilities for mounting communication campaigns. Individual space agencies possess the technical resources for transmission efforts, but lack global authority for such momentous decisions. NASA's Deep Space Network could certainly transmit messages to Atlas, but should American Space Agency speak for all humanity? Similar questions apply to the European Space Agency, China's space program, or any other national organization with relevant capabilities. The message content decisions require even more careful consideration than institutional authority questions. Initial transmissions should probably focus on demonstrating human intelligence and technological capabilities, rather than revealing potentially sensitive information about our civilization's vulnerabilities, conflicts, or strategic concerns. Mathematical proofs, scientific discoveries, and cultural achievements could safely demonstrate human sophistication without compromising security, but even seemingly innocent information carries potential risks. Data about Earth's location, human population, technological capabilities, or resource availability could inform threat assessments by intelligences whose ultimate objectives remain unknown. The balance between demonstrating sophistication and maintaining operational security presents unprecedented challenges for message designers. The response interpretation challenges may prove equally complex. If Atlas responds to human communications, we'll need to develop frameworks for analyzing and understanding alien messages that might reflect cognitive architectures, sensory capabilities, and conceptual frameworks radically different from human experience. Artificial intelligence systems will likely play crucial roles in pattern recognition and communication protocol development. The timeline considerations add urgency to communication preparation efforts. If Atlas captures into permanent orbit around our Sun, we might have opportunities for extended dialogue lasting years or decades. But if it remains only temporarily in our solar system, the window for meaningful communication exchange could be measured in months rather than years. The cultural implications of confirmed two-way communication with extraterrestrial intelligence would eclipse even the discovery that such intelligence exists. Active dialogue would transform abstract philosophical questions about cosmic significance into concrete considerations about humanity's role in a galaxy-spanning community of intelligent beings. Religious and philosophical institutions would face immediate challenges integrating confirmed alien intelligence into existing belief systems. Some frameworks might adapt relatively easily, viewing interstellar communication as validation of cosmic purpose and divine creation's scope. Others might require fundamental re-examination of core doctrines about human uniqueness and cosmic significance. The educational implications would reshape curricula across all academic levels. Students would need preparation for potential careers involving interstellar relations, alien technology analysis, and cross-species communication. Linguistics programs would expand to include xenolinguistics. Anthropology would add xenoanthropology. Psychology would incorporate alien cognitive architecture studies. The security implications of active communication deserve careful analysis. Revealing human technological capabilities, social structures, or strategic interests through communication exchanges could provide intelligence useful for threat assessment by potentially hostile entities. But excessive secrecy might also be interpreted as suspicious or aggressive by civilizations accustomed to open interstellar dialogue. International coordination becomes essential for effective communication strategies. Messages transmitted to Atlas will represent not just the organizations sending them, but potentially all of human civilization. The content, tone, and frequency of communications should reflect international consensus rather than individual national perspectives. The precedent establishment aspects make current communication preparation particularly important. However humanity conducts its first confirmed dialogue with extraterrestrial intelligence will establish templates and expectations for all subsequent interstellar communication efforts. Mistakes made during initial Atlas exchanges could influence alien perceptions of human civilization for generations. The technological development implications could accelerate human communication capabilities dramatically. Requirements for interstellar dialogue might drive innovations in signal processing, transmission power, antenna design, and message encoding techniques that benefit terrestrial communication systems as well. Perhaps most significantly, successful communication with Atlas would confirm humanity's transition from cosmic isolation to active participation in a galaxy-spanning community of intelligence. The psychological and cultural adjustments required for this transition represent perhaps the greatest challenge facing human civilization since the development of agriculture and permanent settlements. The preparation for potential Atlas communication thus encompasses far more than developing transmission protocols and message content. It requires institutional innovation, international cooperation, security planning, and cultural preparation for humanity's potential emergence as a confirmed member of galactic civilization. October 29th approaches. Whether we're ready or not, and the decisions Atlas makes behind the sun may determine whether these communication preparations become immediately relevant or remain theoretical exercises for future interstellar encounters. We stand at the threshold of the most consequential moment in human history, with less than 3 weeks remaining until Atlas disappears behind our sun and makes the decision that could transform our understanding of our place in the cosmos forever. October 29th represents more than just another astronomical event. It marks humanity's first potential encounter with a moment of cosmic choice, where an intelligence from another star system decides whether to become our permanent neighbor or continue its journey into the infinite darkness between the stars. The mathematics of this decision point are as elegant as they are final. Atlas approaches perihelion with precise timing that suggests either extraordinary coincidence or deliberate planning. The orbital mechanics allow for only a narrow window when velocity changes would be maximally effective for capture into permanent solar orbit. miss this opportunity, and the physics of interstellar trajectories ensure that no second chance will come for millions of years. The energy requirements for orbital capture demand exactly the kind of sophisticated propulsion systems that advanced interstellar technology would possess. The 2.3 kilometers per second velocity reduction needed at perihelion represents achievable parameters for fusion rockets, antimatter drives, or even more exotic propulsion concepts beyond our current theoretical understanding. But it also represents technology far beyond anything naturally occurring in comets or asteroids. The timing synchronization with Earth's orbital position adds another layer of strategic precision to Atlas's approach. Solar conjunction during perihelion passage creates the perfect observational blind spot for executing course corrections without human surveillance. This geometric alignment transforms October 29th from a mere celestial mechanics calculation into a masterpiece of operational planning. But the true significance of this moment extends beyond orbital dynamics and trajectory analysis. If Atlas chooses to stay, if it emerges from solar conjunction committed to permanent residence in our solar system, humanity will face confirmation that we are not alone in the cosmos, and that at least some extraterrestrial intelligence takes active interest in other civilizations. The implications cascade through every aspect of human society. Scientific research priorities will shift permanently toward interstellar visitor analysis and communication attempts. International institutions will require rapid development of frameworks for managing ongoing relationships with confirmed alien intelligence. Military establishments will need to assess potential threats and opportunities from technology far beyond human capabilities. Economic disruption will follow immediately as markets attempt to price in the implications of confirmed advanced alien technology. Educational systems will need fundamental restructuring to prepare students for careers in a universe known to contain multiple intelligent species. Religious and philosophical institutions will face the challenge of integrating extraterrestrial intelligence into existing belief systems and worldviews. The psychological impact on human civilization deserves particular attention. Knowledge that advanced beings monitor our development and potentially assess our capabilities will create awareness of cosmic accountability. Unlike anything in human history, future decisions about technological development, environmental management, and social organization will occur with the knowledge that they might be observed and evaluated by superior intelligences. But the psychological effects could also prove profoundly positive. Confirmation that intelligence successfully traverses interstellar distances demonstrates that technological civilizations can survive the challenges that currently threaten human survival. Climate change, resource depletion, social conflict, and technological risks that seem insurmountable might prove manageable, given sufficient advancement and wisdom. The precedent establishment aspects make October 29th particularly significant for humanity's long-term cosmic future. The protocols, institutions, and international agreements developed for managing our first confirmed technological visitor will become templates for handling potentially numerous subsequent encounters as our detection capabilities improve. The Vera Rubin Observatory will soon begin systematic sky surveys capable of detecting interstellar objects monthly or even weekly. If Atlas proves that some percentage of these visitors are technological rather than natural, we could find ourselves managing multiple alien presences in our solar system simultaneously. The frameworks established for Atlas will determine our effectiveness in handling this increasingly complex interstellar neighborhood. The communication possibilities represent perhaps the most transformative potential outcome. If Atlas remains in our solar system and demonstrates willingness to establish dialogue, humanity could begin its first extended conversation with confirmed extraterrestrial intelligence. The knowledge, perspectives, and technologies such exchanges might provide could accelerate human development by centuries or millennia. But the communication challenges also highlight our current limitations and preparation gaps. We lack international consensus on who should speak for humanity, what messages should be transmitted, and how responses should be interpreted. The October 29th deadline approaches whether we're institutionally ready or not. The observational gap during solar conjunction means we'll approach this cosmic decision point essentially blind. Atlas will make its choice behind the sun's protective shield, invisible to our most sophisticated surveillance systems. We'll only learn its decision weeks later when it re-emerges, and we recalculate its trajectory based on whatever changes occurred during the hidden weeks. This enforced uncertainty adds profound psychological tension to an already momentous situation. humanity will spend October 29th knowing that somewhere behind our sun, an intelligence from another star system is potentially making the most important decision in human history, while we can only wait and wonder about the outcome. The point of no return approaches with mathematical certainty. In 18 days, Atlas reaches perihelion. In 18 days, we begin learning whether humanity enters a new era of confirmed cosmic citizenship or continues its solitary development in an apparently empty galaxy. The universe holds its breath as we approach the moment when speculation transforms into reality. Regardless of what Atlas ultimately proves to be, its passage through our solar system has already fundamentally altered humanity's relationship with the cosmos and our expectations for future encounters with objects from other star systems. The questions it has raised, the detection techniques it has inspired, and the institutional challenges it has exposed will influence our approach to interstellar visitors for generations to come. The technological advances driven by Atlas analysis will benefit far more than just astronomical research. The precision trajectory measurements required to detect subtle course corrections have pushed astrometric techniques to new accuracy levels. The spectroscopic analysis methods developed for characterizing its unusual chemistry will improve our ability to study all solar system objects. The international coordination mechanisms created for comprehensive observation campaigns will serve as templates for future collaborative research efforts, but perhaps most significantly, Atlas has demonstrated that interstellar objects can display characteristics sufficiently anomalous to challenge conventional natural explanations. Future visitors will be evaluated with heightened awareness that not everything crossing interstellar space necessarily formed through natural processes. This shift in analytical approach represents a permanent change in astronomical methodology. The Vera Rubin Observatory's systematic sky survey will begin detecting similar objects regularly, potentially monthly or even weekly once fully operational. Each new discovery will be evaluated using the analytical frameworks and institutional protocols developed during the Atlas encounter. The questions we've learned to ask, the measurements we've learned to make, and the international cooperation we've learned to coordinate will become standard procedures. Some percentage of these future visitors will likely display their own anomalous characteristics. Statistical clustering of unlikely trajectories, unusual mass distributions, suspicious timing patterns, or chemical signatures outside expected ranges. Each anomalous object will require the same careful analysis we've applied to Atlas, and some may prove even more definitively technological. The institutional frameworks established for managing potentially technological interstellar visitors will mature through experience with multiple encounters. International coordination mechanisms will become more efficient. Communication protocols will be refined through trial and error. Response capabilities will develop through repeated exposure to similar scenarios. The cultural implications extend beyond astronomy and space science. Atlas has forced humanity to confront the possibility that we are not alone in the galaxy, and that other intelligences might take active interest in our development. Even if Atlas proves natural, the questions it raised about extraterrestrial intelligence and interstellar exploration will continue influencing human philosophy, religion, and cultural development. Educational institutions have already begun incorporating interstellar visitor analysis into curricula. Students are learning about the techniques used to distinguish natural from potentially artificial objects, the statistical methods for evaluating coincidental versus intentional behavior patterns, and the international cooperation requirements for comprehensive analysis. These skills will be essential as encounters become more frequent. The scientific questions Atlas has raised will drive research programs for decades. How common are interstellar objects with anomalous characteristics? What natural processes could produce the unusual trajectories and timing patterns we've observed? How should we modify our detection and analysis methods to better characterize future visitors? What institutional changes are needed to handle potentially regular encounters with technological artifacts? Private industry has already begun investing in related technologies inspired by the possibility that some interstellar visitors might be artificial. Advanced propulsion system research, exotic material development, and long-duration space mission planning all benefit from the knowledge that interstellar travel is at least theoretically achievable. These investments will accelerate human space technology development, regardless of Atlas's ultimate nature. The international cooperation requirements for comprehensive interstellar visitor analysis have demonstrated both the possibilities and limitations of current global coordination mechanisms. The success of multinational observation campaigns shows that effective cooperation is achievable when necessity demands it. but the institutional gaps and coordination challenges exposed during the Atlas encounter highlight the need for permanent international frameworks specifically designed for such scenarios. Perhaps most importantly, Atlas has established a new category of cosmic phenomena requiring systematic study, potentially technological interstellar visitors. Whether this category ultimately contains one object, dozens or thousands remains to be determined, but the analytical methods, institutional frameworks, and international coordination mechanisms developed for Atlas will provide the foundation for studying whatever additional examples we encounter. The October 29th decision point may determine whether Atlas becomes humanity's first confirmed extraterrestrial neighbor, or simply an exceptionally interesting natural object from another star system. But either outcome advances human knowledge and capability in ways that will benefit our species regardless of what future interstellar encounters reveal. The cosmos has shown us that objects from other star systems can display characteristics sufficiently unusual to challenge our assumptions about natural phenomena. As we prepare for an era of potentially frequent interstellar visitor detection, Atlas has provided essential experience in asking the right questions and seeking the right answers. Whatever lies beyond Atlas, we will meet it with greater knowledge, better tools, and more sophisticated understanding than we possessed just months ago when this extraordinary object first appeared in our telescopes and forever changed our perspective on humanity's place among the stars.